Welcome to the first of 4 short lectures about the structure of an aircraft. The structure is one of the main subsystems of an aircraft. In this first video I will talk about aircraft structures in the early years of aviation. Let's start with looking back at the aircraft weight. Last time we saw that the aircraft weight consists of 3 main components: the aircraft empty weight, the payload and the fuel. The weight of the structure is one of the main contributors to the aircraft empty weight. Since we would like to minimize the aircraft empty weight in order to increase the weight for payload or fuel, there is always a drive to reduce the weight of the structure. Because if we can increase the payloads, we can increase the revenues. And increasing the fuel weight increases the range of an aircraft. But what is a structure? And what functions are performed by a structure? I will show this with a simple example. Suppose we are building an apartment building. First, the vertical columns are erected, made of concrete and meant to carry the floors. Then the floors are placed, and subsequently the walls are placed in the building. Often these are prefabricated walls. The whole composition, the columns, the floors and the walls are what we call the structure of this building. The building is not complete. Many systems have to be incorporated, like water lines, electric cables, etc. But the structure of this building is able to carry the loads, to protect its inhabitants, and it can serve as a subsystem where many other systems can be attached to. Aircraft also have a structure with the same functions. Their structures carry the loads, protect the payload, and serves as a framework to attach other systems to. This is illustrated in the pictures below. The picture on the left shows a glider with the lift distribution acting on the wing. The structural elements in that wing will carry these loads and pass it on to the center of gravity of the plane to make equilibrium. The second picture illustrates the protection function. Passengers, crew and cargo should be protected against all kinds of hazards, like crashes or less severe impact of hailstones. Protection is also needed against the cold environment, like a temperature of -60 degrees Celsius at cruise altitude of 11 kilometers. The last picture shows the third function, the capacity of the aircraft structure to provide attachment points for many other systems. In case of aircraft, these are hydraulic and electrical systems, isolation blankets, etc. If we look at the use of structures during the history of aircraft, we can make the overview as presented in this table. In the early times, aircraft had truss structures and wooden wings. These structures were made of steel tubes, steel wires, linen or other textiles, and of course wood. In the 1930s, aluminum was introduced, which is still in use in many aircraft today, although a new era has emerged by the introduction of composite aircraft, like the Boeing 787 and the Airbus 350. In this lecture, we will focus on the early years of aviation. On this picture, you see a Sopwith Camel, an aircraft from the First World War. Looking at this aircraft, we can see a number of typical features. First, the wings, which are very thin. Due to this small thickness, it was very difficult to design a strong and stiff structure inside the wing. Fortunately, this aircraft has 2 wings. It is a so-called biplane. Both wings support each other and provide extra strength and stiffness. This is done by the struts and wires, which connect both wings. The fuselage of this aircraft, although it has some metal plating in front, is made of a truss structure covered by linen. I will come back to this type of structure later. Besides the structural advantage, a biplane had a better maneuverability. But biplanes do not have only advantages. They also had some disadvantages. First, the airflow around wings affect each other. Also, 2 wings result in a higher drag during flight. And last but not least, increasing the wing area by an extra wing does not imply that the wing forces are doubled. The two wings of a biplane offer just 20% more lift than a monoplane. Therefore, in the end, monoplanes got the upper hand. This picture is a very nice example of an early monoplane. It is a replica of a Blériot 9 from 1909. Let's have a look at the very typical structural details. We see the struts and the wires in front and underneath the pilot to support the fragile and thin wing. Furthermore, we can clearly see the wire brace truss structure of the tail. In later years, in the 1920s and 1930s, the thin wings were replaced by thick wings, mainly for aerodynamic reasons. This also gave the opportunity to use the inner space of the wing to create strong and rigid wing structures. These first structures were made of wood, as shown in this picture. Look at the big spar and all the wing ribs with many holes to create a lightweight structure. The skin of this structure is fabric or textile, or sometimes plywood, but it is not meant to carry loads. A very famous aircraft in those days using such a wing was the Fokker 7. This aircraft was very successful in Europe and the United States. The wing was a thick wooden wing covered by plywood, and the fuselage was a truss structure covered with linen. The linen had only a protective function, keeping out the bad weather and the cold. In this slide, you can perfectly see the inside structure of such a Fokker 7 wing. As said, this wing was entirely made of wood, which could only be made by skilled carpenters. Many of them were available in those days. The fuselage of the Fokker 7 was a truss structure. On the picture on the left, you see a full truss structure. In the picture on the right, some kind of wooden cabin is created for the comfort of the passengers. In both cases, the tubes and bar carry the loads and provide sufficient protection. Protection from the atmosphere and partially provided by the linen skin. In this presentation, I showed what a structure is and what its main functions are. Next to that, I discussed briefly some early structures, which mainly featured fuselages made of trusses covered by linen and fitted with wooden wings. This is the first of 3 short lectures about materials and production. As you will see, there is quite some interaction between these two. Also, a third entity, the shape or design, is highly dependent on the type of material and on the selection of the right production process. To start with, what is a material? Although everybody understands what is meant with the material, it is very hard to give a nice and clear definition. Words like matter or substance pop up, although these words are not 100% spot on. So often we need to describe the word material. A material has properties, and these properties are independent of its size and shape. So a material has many mechanical, physical, and chemical properties. For example, a material has density, it has strength, it has electrical resistance. We can determine such properties by taking samples. But in the end, material properties are independent of the shape and size of the sample we analyze. Before, I have discussed the concept of structures. Think about the truss structures you have seen, the beam elements, and the stiffened shell structures. All these structures are made of materials. And some of the properties of these structures are directly or indirectly related to material properties. So we might ask, how are structures made of materials? I will use the following sequence. First, materials are retrieved from ores, which are obtained from the crust of the earth by mining. Or materials are retrieved from, for example, oil by diffraction and processing. Once the material is made, the materials will be shaped into semi-finished parts. Think, for example, about metal sheet which is rolled to thickness on a mill. These semi-finished products, or half fabricates, can be further processed into structural elements like beams. A metal sheet, for example, can be cut and formed into a C-frame. Once we have structural elements, joining these elements together gives us a structure. Today there are many materials. Structural materials can be classified into 4 main groups: metals, polymers, ceramics and composites. Each of these categories have a huge diversity. Metals, for example, have many different groups like steel, copper alloys, etc. And each group has many different variants. There are thousands of different aluminium alloys and grades. Similar diversity is there for other materials, like the polymers or plastics, and the composites. If we look at the basic properties of these 4 main material categories, only metals and composites are used in aerospace applications. However, one ingredient in composites is a polymer. But as pure material, a polymer does not have sufficient mechanical properties to use it in high-performance structures. Ceramics, on the other hand, are strong and stiff enough, but they don't have any flexibility and deformability. Think about pottery. If you drop a vase, the vase will break in many pieces without noticeable deformations. It is brittle. If a metal component is hit and fails, at least it will dent before it fails. So metal alloys and composites are the main materials used in aeronautical applications. They are used because they have sufficient mechanical properties, high strength, high stiffness, and they are not brittle. In the next lecture, we will look at the material properties in more detail.